Okay, in Module 7, I'm going to be discussing the cerebral cortex, or the outer covering of the brain, and our divided brain, the functions of the left hemisphere and the functions of the right hemisphere, a little bit about how they communicate with each other. So this is really interesting because the cortex is the most developed in human beings compared to other primates. So I want to start out by talking about the structure of the cerebral cortex, or outer covering of the brain, the lobes. And there's 4 lobes for each hemisphere of the brain, left and right hemisphere. I'll talk some about the motor and sensory strips, and a little bit about association areas. And I will focus also on brain plasticity, or how the brain rewires following injury, and also how the brain rewires while learning, and how learning occurs and plasticity is greater when we are younger than compared to when we are older. And then function of the left and the right hemispheres, and the difference in handedness. So the cerebral cortex consists of 300 billion synaptic connections. And the brain has a left and a right hemisphere, and you can actually pull them apart. And it's only connected by a band of fibers called the corpus callosum. And this band of fibers allows the left hemisphere and the right hemisphere to communicate to each other. It's the corpus callosum. The outer gray part of the brain, the cortex, is wrinkled in order to create more surface area for the 20 plus billion neurons. So you have this wrinkled mass with fissures and gyri, and that allows for the surface area of the brain to be greater. It allows there to be more brain area. The inner white part of the brain, or the white matter, is due to the axons linking parts of the brain. The axons are coated with a myelin sheath, and the appearance of the myelin sheath gives it the white quality that you see. And we can't just focus on neurons. We have to focus on the helper cells as well, because they're very important. And there are 180 plus billion glial cells, or helper cells, which feed and protect the neurons, and they assist in neural transmission. They're also responsible for forming the myelin sheath. And there's been a great study of Einstein's brain, and Einstein had a regular sized brain. His brain wasn't like 5 times as big as a normal brain. However, Einstein was found to have a greater proportion of glial cells than a normal human brain, and that may have sort of led to his advanced abilities cognitively because of the excess glial cells. So the extra glial cells were able to help him learn or form connections with those neurons more efficiently. So the 4 lobes of the cortex. We have the frontal lobe, which is right behind your forehead, frontal lobe of the brain, involved in speaking and muscle movements. It's also responsible for making plans and forming judgments. And we saw that damage to the frontal lobe, as was the case in Phineas Gage, led to impulsive behavior, and also led to a lack of a filter. So just sort of commenting or doing things that you normally would put a stop to. The parietal lobe lies right behind the frontal lobe, towards the middle of your head on the top. Right behind the frontal lobe, you have the parietal lobe, and this involves the somatosensory cortex. So the sense of touch is the responsibility of the parietal lobe and the somatosensory cortex. Also, the position of your body in space, kinesthetics, is responsibility of the parietal lobe. The occipital lobe at the back of your head is involved in vision. And there's crossover of function for all these lobes. So the right side of your visual field will go to the left occipital lobe, and the left side of your visual field will go to the right occipital lobe. The same thing occurs with the frontal lobe. So your right side of your body is controlled by your left frontal lobe, and the left side of your body is controlled by your right frontal lobe. So that's called crossover of function. And the 4th lobe is the temporal lobe, and these are located at the sides of your heads, where your temples are, sides of your skull. And the responsibility of the temporal lobe primarily is audition, or hearing. Now, within each of these areas, we have specialized tissue called the sensory strips. And in the frontal lobe, at the very back of the frontal lobe, towards the midline of the skull, we have the motor cortex. And once again, there's crossover of function. So left motor cortex controls right side of the body, and the right motor cortex controls the left side of the body. And that's why when you have a stroke, it's generally unilateral, so you can't move one side of the body. So if you have a right hemispheric stroke to the frontal lobe, you're going to not be able to control the left side of your body, and the same for a left hemispheric stroke controlling the right side of the body. If we look at the motor cortex on the bottom of the screen, you see a homunculus. A homunculus is a graphic representation of the amount of tissue in the motor cortex devoted to each part of the body in terms of movement. And as you can see here, the face and the lips get a lot of tissue in the motor cortex, which means that we can make fine and precise movements with our face and our lips. We have more motor control. We can engage in fine motor control for those two body parts. The same thing with the hands and especially the thumb. The thumb gets a lot of tissue in the motor cortex, which means we have very good control over our thumb and our hands. And this is obvious. You can contort your face in various ways, and you can move your face to create all the different basic emotions. The same with the lips. If you ever played an instrument, you know that it requires fine motor control of your lips to produce a certain tone or sound from the instrument. Now, the sensory cortex is located adjacent to the motor cortex, but it's further towards the midline of the skull, and therefore it's part of the parietal lobe. So motor cortex is frontal lobe. Sensory cortex is adjacent to motor cortex, but it's right in back of it in the parietal lobe. And the parietal lobe is involved in somatosensory information, or touch and sensation. And as you can see here, once again, the face and the lips are very sensitive to touch, and so are the hands. While other parts of the body, like the trunk, which is the area of your body between your neck and your stomach, kind of your chest area there, that's not very sensitive to touch. And it's also not very sensitive, or you're not able to move the trunk very efficiently either. So it gets very little tissue in both the sensory cortex and the motor cortex. So the face and the lips and the hands are king when it comes to, or receives the most tissue or the most input when it comes to both motor-based function and touch-based or somatosensory-based function. Here's an MRI picture of the visual cortex located in the occipital lobe at the back of your skull. So if you're looking at a photograph, here's an MRI picture showing activity at the back of the skull. That activity is in the occipital lobe in the what is called the primary visual cortex. And so we can see a lot of brain activity through just fMRI imaging like this. The progression of the cortex, as you can see in rats have very little cortex. Look how small that cortex is. They have the same function of the limbic system and the brainstem that we have, right? They have fear and they have aggression. Those are limbic-based emotions. But they don't have higher cognitive-based emotions like pride. Rats don't have pride. Mice don't have pride. Cat has a slightly bigger cortex than a rat, but a cat and a dog doesn't have pride. I mean, what does pride mean in a cat and a dog? Now, when it comes to chimp cortex is vastly superior to other primates, right? And you see chimp has a pretty similar cortex to human being, and that's because chimp DNA and human DNA are different by a tiny, tiny percentage. And chimps and humans are very close, DNA-wise and function-wise, and their brains are very close. Chimp has more emotion, more complex emotions than a rat or a cat, but I'm not quite sure that a chimp has pride. They may have disgust, but I'm not sure about pride. But chimps don't think about the world the same way humans do. Chimps can use tools, they have some access to language, but not to the complexity that a human being does. And a human being has that complexity because they have the most developed cortex out of any species. The cortex is fully developed, and it allows us to feel a variety of emotions, higher level cognitive emotions, morality, which is not common in animals. It also allows us to engage in complex language and the reading of emotions from language, which is also not available in lower species. The parietal lobe, besides somatosensory information, also has several other functions. And one of those functions is performing spatial and mathematical reasoning. So the parietal lobe, which is behind the frontal lobe, is involved in spatial manipulation, mathematical reasoning, So these are kind of the tasks that you have to rotate a block, and you have to say which of the two three-dimensional blocks or cubes are similar to each other. And you probably had this in school where you're rotating a block in your head mentally, and I have a hard time with it. So my parietal lobe's not working too well with the spatial reasoning part, because that's a very difficult thing for me personally. But it's also involved in mathematical reasoning. The parietal lobe, besides touch, also is involved in kinesthetic information, or receiving kinesthetic information. That's the position of your body in space. And so in order to perform complex motor movements, which you have to do when you're playing a sport or you're engaging in a complex motor activity, you need to know what position your limbs are relative to each other, and that's kinesthetics. And that's another function of the parietal lobe. Temporal lobe, which lies at the side of the head, is primarily responsible for hearing, but also has several other important responsibilities. Temporal lobe has an area called the fusiform face area, or the FFA, fusiform face area, which is responsible for recognizing specific faces. People with problems or damage to this fusiform face area in the temporal lobe may have a disorder called prosopagnosia. Prosopagnosia is the inability to recognize faces. So what people can do is they can see eyes, they can see nose, they can see mouth, they can see chin very easily, but they can't put it together into one coherent whole or into one face. So they recognize individual features, but they're not able to organize them or put them together. And that's one of the functions of the fusiform face area in the temporal lobe. So that area lights up when you show people pictures of faces. But if you show people pictures of objects like houses, that area of the brain does not light up. It seems to be face specific, and therefore probably plays a significant role in prosopagnosia. A good book on prosopagnosia, or reading about it, would be the book of short stories by Oliver Sacks, who is a famous neurologist, and he wrote a book called The Man Who Mistook His Wife for a Hat. It's an interesting read, and if you're interested in brain, which hopefully you are after these lectures, you could read about the struggles of people with prosopagnosia. Temporal lobe also helps manage sensory input related to sound, which helps with the understanding of spoken words. Now, moving on to a very important concept of plasticity. That's the flexibility of the brain. And so if the brain is damaged, the brain will rewire itself, especially if you are young. The younger you are, the more quickly and more extensively the brain will rewire itself following damage. The brain doesn't repair damaged neurons. That's neurogenesis. Neurogenesis is very limited, but it can restore some functions by reallocating brain tissue. So the healthy parts of the brain will take over for the damaged parts of the brain. And once again, it cannot be emphasized enough that this is most easily done when the patient is young. The older the patient gets, the less plasticity the brain has. Plasticity is also involved in learning, so you form new connections in the brain when you learn something. And that's why you're more easily able to learn something when you're very young. So before your teenage years, you're able to learn a language much easier. You're able to learn an instrument much easier. Now, you can learn them as an adult, but it just requires a lot more effort. So this idea that you can't teach an old dog new tricks, this is not necessarily true, but there's something to it, that as you get older, it requires a little more effort for you to learn complex tasks. And that's because the brain isn't as plastic, it isn't as flexible. Plasticity is lowered as you age. And that's also if you have a stroke when you're older, your brain probably is not going to rewire as quickly. The recovery is going to be much more difficult, or you may never recover. But if you have extensive brain damage, a stroke, an aneurysm due to some disorder as a young child, the brain can almost completely recover. And this was shown by the case of a 6-year-old girl who had a hemispherectomy. You could see actually the part of the brain that is scooped out and taken out, removed. Half of her brain was removed to control life-threatening seizures. So usually you have to remove the focus of the seizure, which is the main area of the electrical activity that becomes disorganized. But in this case, the seizure was spreading so rapidly and so aggressively that this girl was having a severe problem doing basic things, and her breathing might have been compromised at some point. So they decided to remove the whole area of the brain that was receiving the disorganized electrical activity, and that resulted in removing half of her brain. And this case was done by a very skilled surgeon that you may have known or heard about from the last presidential campaign or presidential race, and that's Ben Carson. Before Ben Carson was a Republican presidential candidate, he was one of the best, if not the best, pediatric neurosurgeons in the world. And he performed this operation to this young girl. And amazingly, the other half of the brain took over all the responsibility for the removed half or the damaged half. And this girl has almost perfect normal behavior. She has very few motor disability or very few motor problems resulting from the surgery. She was even able to engage in a complex motor activity like ballet, despite having half a brain. So that just shows you that the brain has incredible capacity to reorganize itself, which means it has a lot of plasticity early in life. The same story could not be told if this girl was a couple decades older, even 1 decade older. She would have much more difficulty. But at such an early age, the brain is so flexible that it can take over for this massive amount of damage. Now, I had mentioned earlier that the brain doesn't have specific localizational function. Like, there's not one part of the brain that's responsible for one specific function, like, the grandmother cell theory, right? That this cell is responsible for memories of your grandmother, who she is, etc. That was a long ago held belief that has been kind of put to waste at this point. But the brain has generalized areas that specialize, like the four lobes, and it also has a specialization in terms of the left and the right hemisphere. And the left hemisphere is involved in thoughts and logic. It's also involved in speech, language, and fulfilling in details, so providing lots of details. The left hemisphere also specializes in calculation. So if you think about the logical, calculating language part of the brain, that's the left hemisphere. If you have damage to the left hemisphere, you have problems with language, problems doing calculations, problems providing details. Now, that could be bad, but it could also be good, right, in some way. The right hemisphere is involved in emotion. It's involved in creativity. It's involved in looking at the big picture, looking at the whole. Instead of looking at individual details of each part, you look at the big picture or the whole. It's involved in inferring context or emotion from language. So reading a person's tone of voice. Are they angry? Are they happy? Etc. Are they sarcastic? And if you have damage to the right hemisphere, you're going to have problems with emotion. You're going to have problems with understanding emotion and communication, creativity, etc. Now, people have damage and they keep on living. I mean, left hemispheric damage is hard to carry on day-to-day activities because you don't have any language. You can't understand language. You can't produce language. But people that have left hemispheric damage feel as if they are freed from a prison that they're trapped in, this logical prison, this prison of detail, that they're weighed down by the details of their life. And it's almost enlightening, at least temporarily, to be freed from the weights of all the details of your life, all the planning in your life, that the left hemisphere kind of holds you hostage to. And I'll show you a video clip later on that, in the weekly assignment that will demonstrate this from a neuroanatomist, Jill Bolte Taylor, who had a left hemispheric stroke, and talks about her liberation from the details that weigh down her life, from all the worries and the fears and the anxieties and the future-oriented thinking that we generally have on an everyday basis, that we are prisoners to this detailed logic and this worry that constantly accompanies our day-to-day lives. And everyone has it. It's part of the left hemisphere. And when she had that stroke, she may not have understood language. She may not have understood the seriousness of the stroke to a degree. But she just felt like liberated from her detail-oriented life. And there was part of it that was enlightening, that allowed her to connect with that side of herself that the left hemisphere was suppressing. So It's a really interesting video. I think you'll really enjoy it. I really enjoy it. It's very enlightening. It's very inspiring. It's a great look to have a neuroanatomist look at the damage to her own brain, and the fascination and how she thought about life has changed completely from that point on. So I hope that you get something out of that video. Separating the hemispheres. We know that each hemisphere controls the opposite side of the body, crossover of function. And without the corpus callosum, there can be some problems. The left hemisphere and the right hemisphere don't really talk to each other. Now, the problems are very minimal. You know, it was once thought that if the left hemisphere and the right hemisphere were not connected, that we'd have a huge problem dealing with the world. And that wasn't the case, because they actually severed the corpus callosum in people that had severe epilepsy. And when they severed it, the epilepsy got better, and the person can still function. Now, in a laboratory, there might be some peculiarities, some abnormalities, but in real life, there's almost no difference. And so it's not even worth talking about. If you want to know the specific details in a laboratory setting, you can always Google it or YouTube it, and you'll see some interesting things. But in real life, there's really no difference if the corpus callosum is severed or not severed. Only the left half of the brain has enough verbal ability to express its thoughts out loud. That means if you have damage or stroke to the left hemisphere, you lose language, which is pretty scary. You also lose the ability to comprehend language. Now, handedness this is really interesting, that most people are right-handed and they primarily process speech in the left hemisphere. However, people that are left-handed may process speech in the right hemisphere in a small percentage of. So the left versus right distinction becomes thrown off a little bit in left-handed people. There may be a slight difference in some left-handed people. But since most people are right-handed, speech is primarily localized to the left hemisphere. There might be some genetic or prenatal influence on handedness, that because we are so overwhelmingly right-handed, that left-handers may have some distinctions compared to right-handers. You know, there may be some traits associated with left-handedness more than right-handedness that may have a genetic influence. Left-handedness, for instance, may be more likely to have reading disabilities or allergies or migraines, very interestingly enough. But they also may be more common among musicians, mathematicians, and many athletes and artists. So there are advantages and disadvantages to being left-handed. If you're left-handed, I'm sure you have some really good advantages of this. You probably think some qualities of your life and yourself that you enjoy, but you probably also have some problems just like the rest of us. So I'm not saying that if you're left-handed, you're going to have a migraine or you're going to have a reading disability, but it's a little bit more likely in left-handed versus right-handed individuals, and we're still trying to study why that's the case. So I hope you enjoyed this module. In the next module, we'll be talking more about consciousness and attention. See you soon.